Next on the agenda, Hermitian operators. An operator on a vector space, an inner product space, is called Hermitian if it equals its own adjoint. And likewise, if we have a matrix, we call the matrix Hermitian if it equals its own transpose conjugate. Because if you think of a matrix as an operator on Cn, then its adjoint is its transpose conjugate. So why should we care about Hermitian operators? Well, for one, they're extremely important in quantum mechanics. In quantum mechanics, every physically observable quantity is described by a Hermitian operator. Second, even if we work purely in the world of math, Hermitian operators have some wonderful properties. First of all, if we're working in a finite dimensional space, then all of the eigenvalues are real. And all of the eigenvectors with different eigenvalues are orthogonal. And it's automatically diagonalizable. We don't have to worry about complex eigenvalues. We can always get ourselves a nice orthonormal basis, and we don't have to worry about power vectors. It's always diagonalizable. And we can make ourselves this wonderful orthogonal basis. We've seen how useful orthogonal bases can be, consisting only of eigenvectors. We love bases of eigenvectors. We love orthogonal eigenvectors. We love orthogonal bases. If the operator is Hermitian, we can have both at the same time. So let's look at some examples. Our favorite matrix 2, 1, 1, 2 is Hermitian. You take its transpose and you get the same thing. Take its conjugate, you get the same thing because it's a real matrix. And its eigenvalues are 3 and 1. They're real eigenvalues. And you look at the eigenvectors, and you discover that the eigenvectors are 1, 1, and 1 minus 1. And the inner product of 1, 1 with 1 minus 1 is 0. So orthogonal eigenvectors, real eigenvalues, great. And there's our orthogonal basis for R2. Next, let's look at a slightly different matrix. It's got the same 2, 1, 1, 2 in the corner, and it's got a 3 downstairs. Once again, the eigenvalues are 3 and 1. That's real, so far so good. Only now, you notice that 0, 0, 1 is an eigenvector, and so is 1, 1, 1. They're both eigenvectors with the same eigenvalue, and they're not orthogonal. That's not a contradiction to our theorem. Our theorem said that eigenvectors with different eigenvalues had to be orthogonal. And in fact, the eigenvector with eigenvalue 1 is orthogonal to 0, 0, 1, and it's also orthogonal to 1, 1, 1. So our theorem is satisfied. Now I said we could get a basis of eigenvectors. So how do we do that? Well, we look within the E3 eigenspace, and we just take the vectors we had, and we apply Gram-Schmidt to them. And instead of using 0, 0, 1 and 1, 1, 1, Gram-Schmidt turns them into 0, 0, 1 and 1, 1, 0. These are both still eigenvectors with eigenvalue 3, and they're orthogonal to each other. And they're orthogonal to the eigenvector with eigenvalue 1. So lo and behold, these three vectors are all form an orthogonal set, and we've got an orthogonal basis for R3. Finally, let's look at the matrix 2i negative i2. It's a complex matrix, so you might expect its eigenvalues to be complex. But they're not, because this matrix is Hermitian. If you take the transpose conjugate, the negative I goes here and then gets conjugated to become an I. The I goes here and that gets conjugated to become a minus I. This is a Hermitian matrix. In fact, its eigenvalues are 3 and 1, and its eigenvectors are I1 and negative I1. And those are, in fact, orthogonal. The inner product of I1 with minus I1 is I bar times negative I plus 1 bar times 1, which is negative 1 plus 1, which is 0. Okay. So why should a Hermitian operator have real eigenvalues? Well, if x is an eigenvector with eigenvalue lambda, we can always rescale it to have length 1, and then we compute. Lambda is lambda times the inner product of x with itself, because x was a unit vector. And we can put the lambda inside the ket, because the inner product is linear. And then we replace lambda x with Lx because, after all, Lx is lambda x. And then instead of applying L to the right, we apply L dagger to the left, because that's the definition of an adjoint. It's the thing that applied on the left gives you the same answer as L applied on the right. But L equals L dagger. And Lx is just lambda x. So now we've got the lambda on the left-hand side. And when you pull things out of the left-hand side, you have to conjugate them. And now the inner product of x with itself is 1. And we have lambda bar. So lambda, by this whole chain, was equal to lambda bar. Well, that means that lambda had to be real. So every eigenvalue of an orthogonal, every eigenvalue of a Hermitian operator is automatically real. As for the eigenvectors, let's suppose that x and y are eigenvectors with different eigenvalues. X with eigenvalue lambda 1, y with eigenvalue lambda 2. Then if you take lambda 1 times the inner product of x with y, that's the same thing as lambda 1 x y. Really should be lambda 1 bar, but lambda 1's real, so it doesn't make a difference. And that's Lx inner product with y. But that's the same thing as L dagger x, because L and L dagger are the same. But L dagger applied to x is the same thing as L applied to y. And L applied to y gives you a factor of lambda 2. And so you get lambda 2 times the inner product of x with y. So lambda 1 times the inner product of x with y is the same thing as lambda 2 times the inner product. So lambda 1 minus lambda 2 times the inner product must be 0. But we said that lambda 1 and lambda 2 were different. So this number is not 0. So this number must be 0. We just divide both sides of the equation by lambda 1 minus lambda 2, and we get that the inner product is 0. So we've shown that the eigenvalues are real. We've shown that the eigenvectors with different eigenvalues are orthogonal. And the big deal is that it's diagonalizable, and that's what we're going to show in the next video.